So this video will be for the online virtual class taking MAT 171, and I'm here to talk about 1.1. So first of all, we want to start off before we get into anything algebra related is talk about real numbers. And before we even talk about real numbers, we have to somehow construct what these numbers are. So we're going to start with the most basic, which are natural numbers. The notation for natural numbers is going to be a scripted n, like so. This is your natural numbers. And natural numbers starts off similar to how we count in the real world. That's how they were constructed. And when you count in the real world, you start with the number 1. And then 2, 3, and so forth. The 3 dots that I just drew on the board represents the number set going on forever. So I can't list all the natural number, but you can see the pattern and it would extend forever to the right side. And then eventually, several centuries later, somebody decided to create what's called the whole numbers. This is a scripted W. The whole numbers only has one difference with the natural numbers. And that is, instead of starting at 1, we're going to start off with the number 0. And then it is the exact same number set, with the exception of 0. And it continues on forever. Then going past the whole numbers, we have something called the integers. Integers for z. And the reason why is z is because it's from the German word Zahlen, or Zahlen, which means number in German. And this number set will start from the negative sides. However, I can't draw the lowest negative number, or I can't write it down. So I'm going to draw 3 dots representing the left side, which is the negative numbers. And then it eventually goes to -3, -2, -1, 0, 1, 2, 3, ... Already you see the difference. Integers is pretty much the whole numbers, but with the negative component. So not only do I extend forever on the right side, the left side is also extended forever. So we're almost done constructing our real numbers. We have natural numbers, whole numbers, and integers. Next, we move on to something that a lot of people have heard of, but they quite not, or they don't have the full understanding of it, which is rational numbers. That'll start off with the Q. And I'll use purple for this. Rationals. Now the rational numbers are any numbers or any number that can be represented as P over Q, where P and Q are elements or belong to the set of integers. This symbol that you see next to the Z means belong. P and Q are integers. The only exception is Q cannot be equal to 0. And the reason why is because we don't want a fraction divided by 0. That gets into dangerous territory. So let's write some examples of some rational numbers, because the other sets you were able to see that. However, rational, I didn't give a concrete example. So example, we have 2/3. Why? Because 2 is an integer and 3 is an integer. What else do we have? We have, well, we all know 2.2 divided by 3 in our calculators is represented as 0.666 with a bar over it. Your calculator might round it up, but if it didn't round it up, it would be 0.66 with a bar over it, which represents the 6 will repeat on forever. So, rational numbers are also decimals that repeat. And there are also decimals that terminate/stop. Now, another rational number that people aren't aware of is the number 4. Why is that a rational number? Well, I can represent this as 4 over 1. And then when you see it as 4 over 1 as a fraction, 4 is an integer, 1 is an integer. However, 4 divided by 1 is simply 4. So that still counts as a rational number. Even though it is a whole number, natural number, or integer, we can still count it as a rational. So once we have rationals, we have something called irrationals. There's no notation for that, so I'm just going to write irrationals. And the irrationals are any numbers that are not rational. So think of decimals that never repeat but go on forever. That is the simplest way I can tell you. So an example, the most common example that you'll see is pi. One that we'll be learning in class is square root 2, square root 3, any square root that doesn't really come out nicely. I can't say square root 4 because the square root of 4 is 2, and that is an integer, / whole number / natural number. However, pi, square root 2, square root 3, or square root 2 to square root 3 do not come out nicely. So they will actually go on forever. So we have a nice construction of these category of numbers, these type of numbers. Now, we go on to the big important topic is real numbers. Real numbers is denoted as the scripted R. This is real numbers. And real numbers, I can't really show you it because you cannot count the number of real numbers. But you want to think of it as all of the rational numbers with irrational. If you take all of the rational numbers and then you also account all of the irrationals, that is the set of real numbers. So once we have all this, let's draw a diagram, a visual diagram to see how it looks like. It's a good idea to try to understand this umbrella that we have. So if I draw a giant box that represents the universe, we're going to have real numbers here. The box itself are all the real numbers. Now, you're going to have possibly this portion right here. We're going to call this portion your rationals. That might be a bit hard to see, but I will fix that up. And I just erased everything, but bear with me. This is your rationals. Then, inside your rationals, you have integers. Inside your integers, you have your whole numbers. And then inside your whole numbers, you have the small category, natural numbers. And then outside of this circle completely, but still remaining inside the reals, is your irrationals. They're all over here. So you want to think of it like, hey, my real numbers could be the word vehicles. And under this vehicle, rationals would be considered cars. Under cars, we have integers, which could be represented for cars as, let's say, Fords. And then for the whole numbers, it could be red Fords. And then as you keep going down for natural numbers, you might have red Fords with, I don't know, black tires. Whereas your irrational, they're still vehicles, but they might be a different type of vehicle than a car, like a train. That's how you want to think of this in general. So now that we have shown the categories of different types of numbers, we need to talk about specific properties. And in particular, we're going to be looking at properties for real numbers. So, real numbers, properties. Let's give some example of some real number properties. So the first one is the commutative property. The commutative property. All the commutative property states that if I have, in particular with the properties, we're going to be talking about addition and multiplication. All it's going to be talking about is AB is equal to, A plus B is equal to B plus A. So if we're using addition, the commutative property states that, hey, if I add two real numbers together, I can switch the order. It does not matter. So the example could be 1 plus 2 is the exact same thing as saying 2 plus 1. No difference. That's for addition. It also works for multiplication. So we can say A times B is equal to B times A, thankfully. Then we have the next property. The next property is called the associative property. I'm going to write prop for property. And the associative property states for addition that if we have multiple additions operation, so let's say we have A plus B plus C, it's also equal to A plus B plus C. And what does that mean? So parentheses means that's the operation we're doing first. So we're going to add the first two terms. Then we're going to add the third term. Now, the associative property states that, hey, if I add the first two terms and then add the third term, that is the exact same thing as adding the last two terms, then adding the first term. So we are not rearranging the variables or numbers at all. We are not doing that. That's the commutative property. We are simply grouping them differently. They are still in the exact same spot. I just chose to group them differently. So the power about this is that it also works for multiplication. So we can have A times B times C. If I put them next to each other, that means multiplication. That is the exact same thing as saying A times B times C, where you multiply the first to BC first, then you multiply A. So this might all seem like it's, obvious and everything, but later down the road, you're going to realize things like this aren't too obvious. We're actually happy we have this construction. Sometimes in math, we do not have this at all. And then the last property, the most important one for this class, is, let's do green. Oh, no, I already have green. Let's do red. The distributive property. This is the most important one. Distributive property. What does the distributive property states? Well, it states that, hey, I can have A times B plus C, and that's going to give me AB plus AC. So what is it doing? It is not the associative property where I'm just grouping them differently. It is not the commutative property where I'm rearranging the terms. No, the distributive property relates multiplication with addition. So in high school, you probably are familiar with the whole process of distributing with these arrows. This is a good visual indicator for the distributive property. Now, if you're going in this direction, we call this expanding. There's actually two types of distributive property. Expanding, and then the next one we can have something like xy plus xz, and that's going to give us x times y plus z. Well, if I'm going backwards, which is what I did here, I just used different variables. This is called factoring. And they both fall under the umbrella of distributive property. If I have some certain building blocks and I place them all out, I am expanding it. However, with Legos, for instance, I can break them up together, and that is what we'll call factoring. So that is how distributive property work. We can do an example real quick. So an example with a distributive property. Let's say we have, 5 times 2x plus 3y. If I'm doing a distributive property, it states that, hey, I'm going to multiply this guy and this guy, which just gives me 10x plus 15y. This is expanding. I can also go backwards, of course. But if I went backwards, notice that this is a 10 and 15. They're not the same variable numbers or anything like that. We'll discuss that more in 1.3. But we can still do that later on. So that covers the distributive property, which is very important. Now, I want to make sure that we understand one last thing about real numbers, which is negatives. What are negatives? How do they operate? All of that stuff. So negatives are just the inverse of addition. If I have positive 7, that means I add 7. However, the negative version of it is going to be subtract 7. So negatives are just subtraction, really. However, we might have some complicated stuff like this operation. What happens if I have a negative times a number? A real number A. Well, we're going to say that a negative times a positive number will give us a negative number. Now, I never said, or, it's not explicit that A is strictly negative. It could have been a positive number or a negative number. I don't know. If that's the case, I can literally say negative of a negative number can give me a positive number, which is A. And if you see a negative by itself like that, you can always assume this is a negative 1. That's always an assumption we make. So I have that. Great. What other properties do I need to know about negatives? Well, you need to know what happens if you have a negative number times a negative number. Well, if you ever have this, where we can actually treat this as negative of negative AB, which is going to be what we used over here and over here. And that'll give us positive AB. So a negative number times a negative number will give us a positive answer. You still have to multiply them, but it gives us a positive answer. That is the idea. And then the last part about negatives, what if you had negative times A plus B? Well, that just means we got to distribute it over. We can treat this as a negative 1 and distribute the negatives over, which will give us negative A plus negative B, which this is the exact same thing as saying negative A minus B. And I want you guys to be aware that they are the same. They are equivalent. So already we discussed categories of numbers right here. And then we also discussed properties of numbers. And then we also discussed, hey, if I have negative numbers, what property do they have? Which are over here. Now, I want to do something that we all missed on the diagnostic assessment. This is called set builder notation. And a set is just a collection of objects. So we're trying to build a collection of objects. So there's some language we need to discuss. So a common language that you'll be seeing in the class is something along the lines of a curly braces with these symbols. Oops. I don't want to do that. Instead, I want to do this. Such, let's see. Let's do 0 less than or equal to x and 7. You need to be able to tell me, hey, what are the collection of objects inside this, I guess, language? This hieroglyphics or whatever is telling us specific numbers, and it wants us to spit out those specific numbers. Well, here's how we're going to read this. The first component right here, that's an x, so that's clear. However, the second component we might not be familiar with, that means belongs to. And then from earlier in the categories, we know this means natural numbers. Now, we have x belongs to natural numbers. Great. But what does this line right here mean? Well, this actually just means such that. Don't ask me why. It means such that. So if we read it, it says x belongs to the natural numbers such that x is in between 0 and 7. If we list out those numbers, so x has to be a natural number, and it has to be between 0 and 7. Those numbers are 1. So I'm going to put equals. Oops, that's not a good equal sign. This is actually equal to 1, 2, 3, 4, 5, 6. All of these are natural numbers. Now, notice I didn't include 0. 0 is not a natural number, so I cannot write that down. Even though it says less than or greater than or equal to 0, I cannot include it because it's not a natural number. I also didn't include the number 7 because this symbol less than is a strictly less than symbol. It is not less than or equal to. It is less than 7. It has to be a number smaller than 7. It cannot be equal to 7. It has to be smaller. And the smallest number next to 7, that is a natural number, is going to be 6. So this is the collection of objects we are looking for. And you can bet this is going to probably be on a test. That covers for set builder notation. And then there's one other type of notation we need to understand. Set builder notation is really good for finding the collection of objects. Now, the problem is, hey, what if our collection of objects is on a number line, per se? You can still do this. But on the number line, like so, if I were to draw a number line 0, 1, 2, 3, -1, -2, -3, and let's suppose I drew a circle here, I colored it in, and then I want all the numbers from here all the way to here. And I want to write that in interval notation. An interval is a specific time that starts to where it ends. So we need to find the starting point and where we need to end at. Notice that we started at -1 and we ended at 2. However, on -1, the circle is colored in. That means we want to include that number. If it's circled in, we want to include it. Include. Now, we are still including 0 and 1, but the thing that we start off with is -1. And we are including -1. However, the number that we're ending at is 2. The problem is it is not colored in. Because it is not colored in, this will signify not include. So we want to include -1, but we do not want to include 2. Our lowest number is -1. Our highest number is 2. You always go from lowest to highest. So we're going to write -1, comma, 2. That's where our interval starts and ends at. It might not hit 2. We might not want to, but it does end near there. It doesn't end exactly at 2, but it ends near there. So what I mean is that we can get 1.9999. We just can't include the number 2. Now, the symbol for including in interval notation, this is interval notation. Can I write that down? Interval notation. The symbol for interval notation, if we want to include a number, we're going to be using brackets. If we don't want to include a number, we're going to be using parentheses. So what this means is that I want to start and include -1, and I want to get all the numbers between -1 to 2. Every single number in between -1 and 2, I want. However, I do not want the number 2. So I'm going to stop at 2 and not include 2. And that is what the parentheses mean. Include, not include. So, let's do another practice. Let's say, for instance, I had something a bit more complicated. So -6, -5, -4, -3, -2, -1. And this time I have this. Now, do you see that these two lines, this time I drew 2 lines that I want, two collection of objects that I want. But I should only have 1 collection, even though there's 2 lines. So how do I do that? Well, first let's just deal with the first collection of objects, the left side. I start at the number -6, and I stop at -5. Now, they're both open circles, and think of the open circle like, hey, I'm missing that number. That's why I didn't color it in. So you want to use parentheses. Parentheses means you missed out on that number. And then if we work on the second one, we start at -3 all the way to -1. All the way to -1. And because the circles are circled in or closed in, we're going to use brackets to include them. Now, this is great. I have the collection, 2 collections of objects, but I need to treat it as a single collection. So I use a symbol called union. This is called union. Union. What the symbol union means is that you're going to combine them together. So even though we see 2 collections of objects, this is treated as one entity or one collection. Boom. This is how we can describe the number line in interval notation. You can do it in set builder notation, but that's a bit of a challenge. And then we got a few more things to talk about. We only have like 2 more things, which are fractions and knowing what absolute value does. So let's talk about fractions. Fractions. If I have a fraction, let's say, if I have a fraction that, I'm not going to use numbers because those will go into examples. So I have a fraction. I want to add them together. I want to add them together, and if we notice our denominator or our lower number is the exact same, I can just add the top and keep the denominator the exact same. The denominator must be the same value for you to add fractions. So example, let's do 3/5 plus 1/5. 3/5 plus 1/5, because The denominators are both 5. We're able to add the top together, which is 4 over 5. That's our example. This is the exact same with subtraction. So I'm not going to go into subtraction with that. Now, what if they're not the same? That gets a little complicated. Some of you guys may have heard of least common denominator, but we'll talk about that later on. For the moment, if the denominators are not the same, we're going to do it the long way. We'll learn about least common denominators soon. So I have A, B plus CD. So the denominators are different. How do I deal with this? Well, there's the idea where, hey, if you can't find the least common denominator easily, what you can do is I can say that, hey, this is the exact same thing as saying B times D. What is that? A plus, oops, I apologize, let me fix that. That is the exact same thing as saying, hey, my new denominator, that is going to be the same, if I multiply them by a number, will be B over D. And all I did was I multiplied this guy right here by D over D, and I multiplied this guy by B over B, which is the same thing as multiplying it by 1, because if you multiply something by 1, it does not change the value at all. So I have DA plus CB. That is the exact same thing. Let's do an actual example so we understand this. Example. Let's say I have 5/7 plus 3/5. Well, the least common denominator is what we're going to get regardless. So let's just do what we did. I have a 7 denominator and a 5 as the denominator. They are not the same. So what I'm going to do is I'm going to multiply them together. 7 times 5. Now all I have to do now is multiply this guy by 5 over 5. And I multiply this guy by 7 over 7. I get these numbers from the denominators. They are the denominators. Let me use a different color. So that way, if you guys refer to notes, this isn't confusing. 5 over 5 and 7 over 7. The idea is that you're normally going to multiply the other term by the denominator over the denominator. So I have 5 times 5 plus 3 times 7. All under this. And if I simplify that out, that gets, what is that? I get 25 plus 21 over 35. And that'll give me, there's a 1 by the way, that'll give me 46 over 35. Now you can change it into a mixed fraction. I do not mind. For now, we're just going to leave it that way. I am a big fan of improper fractions, and it makes life easier. So that's how you add fractions with different denominators. How do you multiply them? How do you divide them? Well, let's talk about that. If I want to multiply them together, let's say I have, A over B times B over C. The good side with multiplication, the denominators really do not matter. They only matter for simplifying. So when I multiply this out, all you have to do is multiply the top row together, the top together, and you multiply the bottom together. That is it. Now you might have to simplify. Did I do this right? Let me make this AB, make the CD to make my life easier. So we have no confusion. CD, so we have AC over BD. Example, let's say we have 2/7 times 4/8. If I wanted to simplify that, we just do 2 times 4 over 7 times 8, which is going to give us 8 over 35. That is it. Multiply the top with the top, the bottom with the bottom. That is how we multiply. Now, I will talk about division because that might cause problems. Subtraction, not too big of a deal. But division, it does cause a lot of confusion. So let's go with that. If I wanted to divide, this symbol is the symbol for division as well. There's multiple symbols for division. Not only can I do a fraction symbol, but I can also use that symbol right there. C over D. All we have to do if we divide things out is we're going to instead change it to multiply. Multiplication. So we have AB times. So there's a common phrase that people say is keep, change, flip. We're going to keep the first term the same. We're going to change the symbol division to multiplication. And then we're going to flip or reciprocate, that's the bigger word, our value C over D. It's going to turn into D over C. That's what it means to flip / reciprocate. I will be using reciprocate from now on in the class instead of the word flip. So if I do that, it's multiplication. And when we multiply, we just multiply the top with the top, the bottom with the bottom. AD over BC. So let's do an example. Example, if I have, let's say, 4/9 divided by 1/2. This is the exact same thing as saying, I'm going to use a different color now. 4/9 times 2 over 1, because I change it. I keep the same term. I change division to multiplication, and then I flip the second term or reciprocate. And I'll turn into 8 over 9. Oh. That is how we do division. Then the problem comes when it becomes a compound problem. The word compound just means, hey, it's simple with an additional step. It's not nearly complex. Compound just means it has additional steps. It doesn't have to be a lot of additional steps. It could be 1, it could be 2, it could be whatever. So, a compound problem you might see, and I think this is actually in your homework, something along the lines, is 1 plus, let's do 3/2 divided by 2 minus 1/4. That looks crazy. That looks silly. So the way we're going to tackle this is we're going to tackle it into pieces. We're going to look at the top and the bottom. The top is this piece right here. The bottom is below that. So if I calculate the top, 1 plus 3/2. Well, 1 can be represented as a fraction or a rational number as 1 over 1. So let's write that down. We can write this is equal to 1 over 1 plus 3 over 2 divided by, well, 2 can be represented as 2 divided by 1 subtracted by 1 over 4. Now, they have different denominators. So we got to find the least common denominators. Well, using our rule earlier, we can just multiply this guy by 2 over 2. Multiply this guy by 1 over 1. Multiply this guy by 4 over 4. And then multiply this guy by 1 over 1. Then I have 1 over 1 plus 3 over 2. 2 over 1 minus 1 over 4. Oh. And if I calculate this out, it actually isn't too bad. 2 times 1, the very top of here, is going to be 2. Oops, let me use a different color. I keep using the same color, which can be confusing. Green. There we go. It'll be 2 over 2 plus 3 over 2. And we're going to divide that by, divide that all by 8 over 4 minus 1 over 4. So all I did was multiply them out. Now we we made some progress. We can actually do the top piece now. 2 over 2 plus 3 over 2, that's going to give us 5 over 2. They have the same denominator, so we just have to add the numerators. The bottom part is 7 over 4. Boom. Now, we have to recall, this symbol right here, this is division. Division. Oh, my handwriting is getting sloppier. It is division. So I can write this as 5 over 2 divided by 7 over 4, which is the exact same thing as saying 5 over 2, keep change flip, times, reciprocate it, 4 over 7, which will give us 20 over 14. Now, of course, we can simplify that into 10 over 7, but that's another day. I don't feel like talking about simplifying just yet. So that's how you do compound fractions. You want to calculate the top, the numerator, and then the denominator as much as possible, and then replace that division symbol with the other division symbol, so you can keep track of things better, and then keep change flip. That is how you do division. Now, with the interest of time, we have to call it a day. The only thing I didn't talk about was absolute value, but we'll talk about that tomorrow. And don't worry, you guys are not behind. My actual in-seated class has yet to talk about compound fractions and absolute value. So we're making good progress, actually. And if you're too stressed about the homework, don't worry, the homework is not due till next week. That is the reason why. Now, you do have the WebAssign homeworks and the Getting Started homeworks, which most of you have already done. However, the homework 1 from WebAssign, it is not due till Tuesday for a reasoning. I am going to upload these videos for each section. That way you guys can follow along and make sure you guys don't fall off too far. Okay? So, I'm going to upload these set of notes and this recorded video for you guys on Blackboard. So I will catch you guys later. Take care.